clearly. Okay. So this is a different format of a talk than what I am going to do in the afternoon and tomorrow. The talk that we're going to do today, I've done 2 times before at meetup groups. It's usually a 2-hour talk. There's a lot of live coding involved, and it's usually for a much smaller group. So we have the advantages of not having a strict time limit, the advantages of being able to do this in a very participatory fashion. With a group this large, I would still like to capture a little bit of that participation, so please feel free to ask any questions. But there is, in my mind, a kind of order that these go in, and we do have a limited amount of time. Once we're done with this talk, so I'm going to be live coding an IPython notebook to show some examples. Once we're done with the talk, I'll take that IPython notebook and I'll send it around to all of you guys. Before we get started, I'll say that if any of you are not using IPython notebook, especially if you're academics or researchers, you should go ahead and start using it. You'll see it's an incredibly useful tool for doing exploratory programming in Python. And one thing that you may realize is that IPython notebook is very difficult to get installed if you're running any sort of custom setup, because you need to install Python ZMQ, Python Tornado. There's a lot of dependencies. So I will say right now, if you are, especially if you're a researcher or an academic or a desk quant or somebody who uses Python as a tool for doing some live scripting and live coding, go to continuum.io/downloads and download Anaconda. It is a Python distribution that comes with matplotlib, numpy, scipy, IPython, Numba, and a million other packages that you might use. And it is incredibly easy to install, and it will eliminate almost all the headache of getting a working Python system installed on your computer, especially if you're using Mac. You don't have to deal with Homebrew or any of that nonsense. On Linux, you may find the situation is a little bit easier, but I really recommend if you're on Windows or Mac, this is a very quick and very useful way to get started. And that's my pitch for you guys. Just to introduce myself to those of you who I haven't already met or haven't already had the pleasure to meet, that's the 4th thing you should do, suck up to the audience. That really works in talks. I'm James Powell. I'm from Houston, Texas, but I moved up to New York City a couple years ago to work. When I say New York City, I realize when I'm back in Texas and you say New York City, you shouldn't say New York City, you should say New York City. No, if any of you remember the Pace Picante commercials from like the mid-90s. In New York, I run the New York City Python meetup group, which happens to be the, let's take a look, in the world, the 6th largest meetup group. And we have 3,546 members. So if I refresh this page and it goes up, then I know I'm doing a good job. If it goes down, then maybe I better get back to New York as soon as I can. This is me right here. There is, as you may have all realized, there is an enormous amount of interest in Python in the academic community, in the research community, in the finance community, in the web programming community. In New York City, this is no exception. There is so much energy and interest and so many things going on. So I encourage all of you, if you ever find yourself in New York City, please look us up, send me an email, drop by. We have anywhere from 2 to 3 events a week. Every 2 weeks, we have a big event for 125 people where we give talks. We have a lot of great speakers like Mike Bayer from SQL Alchemy, Zed Shaw. We have the guys from Continuum Analytics, the guys behind NumPy and SciPy. This month, I don't know if it's posted yet, we have the schedule hasn't been posted. We have a night of talks at a startup called, or at a co-working space called Protective Space. We will have the managing director of Continuum Analytics talking about Python and finance, and we'll be giving away a very interesting book about quantitative finance using Python. So that's who I am, and that's what I do. I also have a blog, which I haven't updated since, unfortunately, the 7th of May, since speaking schedule has been very aggressive. I really like the domain name that I got. I got don'tusethiscode.com, since this is maybe a reputation that I've built for myself over the last few years as somebody who has examples of code that maybe you shouldn't use. Smartly, I put the blog on a subdomain, seriously.don'tusethiscode.com, and I consider that to be a sufficient disclaimer. So I usually blog about some pretty weird stuff. This is implicit self using eval. The third part of this, which I haven't posted yet, requires doing some bytecode hacks and to go into the running interpreter and to flip flags and to change things at runtime to make closures mutable and to flip flags on functions and to replace bytecode live. It's not something that you should do, but I think that I think that as you push the boundaries of what you can do, you learn more about what you should do, and you get a lot of texture and the contours of what's available to you. My personal, and we'll see this in this talk as well, my opinion is that we learn by pushing boundaries, and there may be things that we can do that we never should do. But knowing what we should do, knowing our limits, is one of the best ways to get a real sense for the core of what we are doing day to day. So a lot of what I may show you in terms of examples aren't things you ever want to do in production code, aren't things that you might want to subject your coworkers to. But I think that there is something still to be gained, some value there in looking at the extents of the system. Also, I should say that my fundamental philosophy about these kind of things is that as a programmer, we are all very engaged, enthusiastic, and idiosyncratic people. We have ways that we think we should do things. And we have in our minds a view of what the most important parts of a problem are and where sophistication is valid and where sophistication may be overblown. And to that respect, somebody may come up to us and say, we want you to solve this problem. And we may say, well, this is actually a very, very hard problem, and we need to apply an enormous amount of sophistication to solve it correctly. And in order to do that, we need to use these advanced structures, these very sophisticated structures, decorators, generators, context managers, metaclasses. And others may balk. I think the proper way to resolve this problem, and I think this problem has come up for all of us continuously in our careers, is that first, we shouldn't be afraid of sophistication, but we should keep in mind that there are some liabilities that we incur when we try something that is a little bit non-standard, or when we reach for something, which isn't to say that we shouldn't reach for more sophisticated tools, but that we should keep in mind when we do reach for them that there may be consequences that we aren't already aware of. Additionally, I think that more fundamentally, as developers in an organization, we should be willing to subordinate ourselves to the goals of the organization to some degree, which means that in this talk, I'll show you some things that I prefer to do in the code that I write for myself. But in an organization, if there is an organization-wide edict, such as don't use property, don't use descriptors, don't use this, to some degree, I think that it's worth subordinating what you think needs to be done to the broader goals of the organization and playing along with your fellow developers. So we need to balance these things, and that's another disclaimer for this talk. So let's get started. So I'm going to be doing some live coding in IPython Notebook. I like to walk around a little bit. One reason I use IPython Notebook is that I've given this talk live coding from the terminal, and with a crowd this large, with how nervous I am, and also I'm a little bit sick, I figure that I'm going to fat finger like a million different times, and it's going to get very confusing for you. So at least with IPython Notebook, I'll be able to, backspace. I have some just basic notes about the order and the structure and the themes that we'll be talking about, but outside of that, this is a talk that I've given a couple of times, and I have a flow for it in my mind, but I'm willing to go off on a divagation if time permits, if there's a particular area of interest for any of you. Unfortunately, this crowd is way too large for me to poll you for any particular interest or areas where you might be interested. Also, I think that the speaker in the other room has not shown up, so that a bunch of you are here because there's no one else to listen to, which I'll take that. I'll take anything. So the broad themes that I want to talk about, before I get started, the fifth lesson of giving presentations that I've learned is that people may sit through your presentation. They may be enraptured. They may love it. And they'll come up to you at the end of the presentation and say, that was the best presentation I ever saw. What's your name again? So, my name is James Powell. I like to repeat my name a couple of times because, I find this happens a lot. If you want to reach me, if you want to speak to me, you can email me at james@nycpython.com. If you're ever in the city and you're interested in meetup groups around Python or Flask, I run the NYC Python meetup group, and I co-run the Flask meetup group. And if you're interested in blowing a couple hours on a weekend, you can read my blog, seriously.don'tusethiscode.com. So the themes that I want to go over today, there are a couple of broad and kind of mixed themes, and some of these are higher level and some of these are lower level. One of the high level themes I want to share with you is a view of the interpreter that recognizes that the interpreter has a certain type of static ignorance. The interpreter really doesn't know a lot about the code that it's running in a static context. And what I mean is, you give the interpreter a line of code, and it really has no clue what's going on with that code, with any information, it has no idea what's going on with that code without some of the information provided by where that code's running dynamically. An example of this is decorators. So you have that @ symbol and the name of a decorator, and then you have a function body. And I have a patch that I blogged about where I loosened the restrictions on what can come after the @ symbol, and I made it so that any arbitrary expression can come after the @ symbol. And all I had to do was loosen the restrictions in the grammar, and everything worked from there. The reason for this is when the interpreter sees an @ and then some expression, it doesn't know what that expression is statically. It could be anything. There's no static constraints on what that expression has to be. And as a consequence, the interpreter has to treat everything that it sees in the same unified fashion. It has to go through the same checks. Similarly, if you have some name and then parentheses around it, and you say that's a function call, well, the compiler doesn't know that that's a function object. It doesn't know it's a C function object. It doesn't know if it's a class. It doesn't know if it's a generator. It has no idea what that is. So in every single case, the interpreter does the exact same thing. It uses the call function bytecode in order to invoke that. And the call function has to go through these steps of determining what is that object that I'm actually calling. The interpreter, it turns out, doesn't really have a lot of information. In C++, the compiler has enough information to say this is, at compile time, with no information about the running program, it can say this is a class, and you're invoking a class. You're invoking a class to create you're invoking the value constructor to create a value, an instance of the class. Or the interpreter is able to say this is a function, and this function is short enough that I can inline it. Python doesn't have that ability. It doesn't have that information. It's actually a very ignorant compiler. And the ignorance of this compiler is what allows such a broad, it gives us this opportunity for such dynamic behavior. The next theme I'd like to talk about, and one of the themes that I think is fairly poorly documented, is that we come, in a talk about metaclasses, we probably all have an opinion that metaclasses are a little bit magical and a little bit weird. And this may be true to some degree, or historically this may have been true. But I think that we can refine our understanding of this concept and to begin to view metaclasses as merely yet another tool to get a very specific job done. So if somebody comes to you and says, decorators are kind of weird, why would I want to use a decorator? Or context managers are kind of weird, I want to use a context manager. We can all argue for the use of a context manager. We'll say if you have some setup and some teardown, and you want to always set up first and you always want to tear down later, that's what a context manager is. That's what it does. With a decorator, you can say if you have some common code around a function, if you have what they used to call aspect-oriented programming back in the 90s, use a decorator, and that's your tool for getting this done. Metaclasses are actually a very specific tool for getting one job done, and they're the only tool in Python that can get this job done. This job being enforcing a constraint from a base class to a derived class. And we'll talk about this towards the end of the talk. The next broad theme I'd like to talk about, and these two go together. I'm actually fairly new to Python. I've been doing this only for a couple of years. But one thing that I found to be enormously helpful in getting a very deep understanding of the language is looking at the CPython interpreter. And I'd like to say two fairly controversial things. First, this isn't the controversial part yet, but the first part is that Python is a language without a spec, without a written specification. If you go online and you look for C++ TR1, you'll see a multi-thousand-page spec that you have to pay for that details all the different interactions of features in C++ and all the different things that a C++ compiler implementer has to be aware of. And there are, I have a friend who's really big into C++, and he went off to work on LLVM at Apple, and he used to tell me about this 20-year-old guy on Stack Overflow who had read all the standards cover to cover and could quote sections by heart. And that's kind of impressive, but we don't really have that in the Python community because Python has only a reference implementation. It doesn't have a strict spec. So I think that one thing that we can, so the controversial part of this is to view CPython, the interpreter, as a reference implementation of Python and as a guidance for how the language is supposed to work. So for example, if you have some code and it works in CPython and it doesn't work in PyPy, I think that it would be fairly natural for you to assume PyPy is broken, CPython's the right behavior, except in some fairly exceptional circumstances. And this is a controversial perspective, but I think that we can use CPython as our reference for how the language is supposed to work. The implication from this is that if we read through CPython and you understand the interpreter, that can give us guidelines for saying specifically what happens in different cases. So for example, if I were to make a descriptor a metaclass, if I were to look at the intersection of some weird features, some sophisticated features, in C++, I'd have to look in the spec and I'd have to get my rules lawyer out, my 20-year-old German rules lawyer out, and I'd have to ask him what happens when we combine these two things. And he'll say, well, the spec says explicitly this, but the spec is missing this part, and this is undefined. And historically, these compilers have done this, and historically, GCC has done that, or G++ has done this. And it would be more of a negotiation for what the correct behavior is. I think that we can get an understanding for Python by understanding what the CPython interpreter does and say that's actually how the language is supposed to work. And we're going to look into that when we look into how metaclasses actually work. And that's the perspective I take. The second thing is I'd really like to encourage you to look at the CPython source code and to use that as a source for better understanding of the language. To read this source as frequently and as often as you can. Because I think that you can gain a lot of expertise, you can gain information about the language in a very short period of time, a lot of depth with the language in a very short period of time, just by reading through different parts of the C code. And I'll show you one or two tricks. In the 3 talks that I'm giving today, in the afternoon, and tomorrow, I'll show you a couple of tricks for how you can do that effectively without even needing to know where to start. You can just grep for certain things, and there's a nice entry point. And when you start reading through the code, you'll see that it has been written in a very simple, straightforward style, without a lot of onerous optimizations, without a lot of unnecessary complexity. It was written in part for simplicity of implementation and readability. So it's actually a very useful tool. And the last theme that I'd like to cover, and these are themes that I'll probably cover in all of my talks in PyTexas, is a view of Python as a system for building systems that do real work, but to perhaps blur the line between where the language ends and where your application begins. Because I think that, especially when you look at metaclasses, you can begin to see that a lot of problems that you want to solve can be modeled not in terms of constructs that you've written yourself at an application layer, but constructs that you write into the interpreter, or tools in the interpreter that you use. So one example of this is, we've all seen systems that have fairly complex configuration mechanisms, where you have configurations in some file here, in like an INI file, and you have some overridden configurations over there, and you pass things from the command line, and all sorts of things like that. And the way to get that to work, somebody wrote a library that parsed the file and asserted different validations on the configuration, and they wrote a configuration validator, and all sorts of mechanisms. This was a lot of Python code written in the application layer. But I think that there is an argument to say that, well, we already have a lot of the tools for modeling what you need in a configuration system in the import system, and that you might be able to build a configuration mechanism, a way to configure the application, by writing your configuration parameters in pure Python files, and then having an import hook that performs the validation or that performs the tasks that you would otherwise have written into code. And the difference here is that instead of writing things at a very high level, instead of stacking code on top of the language, you're writing code in a more symbiotic relationship with the language. And I think especially with metaclasses, we can see that this can be a very fruitful technique, although it tends to be something that we don't see often in practice, and something that may require a slightly higher degree of sophistication. However, I would argue that it allows us more confidence, and it results in code that is a lot more robust, because we're better making use of constraints and guarantees and testing and heuristics and protocols that were built for us, as opposed to having to build them ourselves. So those are the broad themes of this. The order in which I'm going to talk about this is, I want to talk about the contours of classes. So just to give you guys a brief overview of some of the interesting things and different things about classes. This is going to be about beginner to intermediate. So if you hold on a little bit, we'll get to the really weird stuff in another 15 minutes or so. I'd like to talk about the class construction mechanism, so how classes actually come into being. And we'll look at some code in the CPython interpreter for that. And then I'd like to talk about what metaclasses are, and about this ability to constrain something from the base class to the derived class. And then at the very end, if we have time, I'd like to show you some interesting new things in Python 3000, such as prepare, and how you can write your own simple enum and things like that. So first off, we're going to be doing this in an IPython notebook. And the very first line I started with is sys.versioninfo, just to show you that we're doing this all in Python 3. I do the majority of my work in Python 2, so I may make a couple of mistakes, but I was encouraged when talking to Nick yesterday that maybe all presentations from now on should be using Python 3. And at least that'll allow for one more person in the world using Python 3, making it a total of 6 or so. Now, is Nick in the room? Because I don't want to get in too much trouble. Oh, he's not. So we can really slam on Python 3 if we want. No, it's actually, you'll see that Python 3 is a better language than Python 2. And that if you're still using Python 2, the best reason to still be using Python 2 is because you have no other choice, not because you prefer it. Because I think in many cases, Python 3 is a much better language. So I want to go over the contours of classes. And one example that we're going to use throughout this is, I don't know if any of you guys ever played MUDs back in the 80s and 90s. So we're going to look at classes that you might see in a simple role-playing game, mobs and objects and players. I think that's a fairly compelling way or a motivation for how to look at some of these constructs. So I'm going to just breeze through as many of the contours of classes as I can. If you have questions, shout them out. But let's see if we can kind of weight ourselves towards the more novel parts and maybe kind of get through this as quickly as possible. I want to make sure that everybody is on about the same page. So this is a simple class that represents I made the first mistake. In Python 2, you have to derive from object to get a new style class. In Python 3, there are no old style classes anymore, so you don't have to derive from object. This brings up one important topic, which is the actual mechanism of how classes work in both Python 2 and Python 3 is actually very broad and very deep. And there are a lot of interactions that we don't really have time to go over, such as how do you resolve if you overload addition, and on two classes, how does it resolve which addition function? Is it using radd? Is it using regular add? And that is a little bit complex, but in most cases, we don't really run into that complexity. So I'm going to try and show you the contours of what, in real use of classes, we have a much more narrow view of the complexities and the problems that we run into, and I want to focus on those. So we have a mob, and the first thing that we might do is write an init function. So we know that classes have these underscore functions, and these underscore functions are essentially implementations of a particular protocol. We know that with classes for the construction of the class, the value construction of the class, we have both a new and a init. And we know that new gets triggered before the class is constructed, and init is initializing the class. So the first argument to new shouldn't be self, it should be CLS. And we generally only really run into the use of new when we're doing things like subclassing from int or some of the built-in types. Or if we're trying to do something like have a singleton, or we're trying to enforce some additional outside behavior on the construction of this class. For the most part, we just use init. So I'm going to just use our simple, and we're going to do this in the junky style, as opposed to using super. I don't really want to talk about super. I think there's a lot of opinions about whether super is good or bad, and the changes to super in Python 3. I don't really want to get into that. Personally, I feel that super is good at very limited things, but it has a lot of holes and a lot of strange behavior, especially when you try to use super with, for example, properties that you've overloaded. So this is a mob, and it's just a monster, right? So maybe the monster has, well, this is a mob. So the mob represents any mobile object in the game. So this is actually our base class. So the mob may have an x and a y coordinate, and it may have nothing else. So, right? Simple enough. When we start to create our monsters, we might have our monster derived from mob, and the monster will add hit points, and it might add a name. And then if we have subclasses of monsters, we might have hit points and a name and other fields as well, like special abilities, something like that. We might also have, so what are the common things that we see on classes? We see the use of these underscore methods. So the most typical ones that you'll run into are these four. Here I'm going to do something pretty cheap. And here I'll just do, actually I'll do this the proper style. And I'll show you why this is the proper style. Well, this isn't really the proper style, but. So this is how you might want to write this. Well, And it also illustrates something new to Python, well, something fairly new in Python, which is, there we go. So let's create a mob. And, oh, and we have to create it with its location in space, so it's at the origin. Here we go. And there's a couple of small things that I did that might be of interest to you. Notice I'm using the newer style string formatting, and I'm using the attribute lookup in the string formatting, so I only have to pass it self, and I can actually look up the attributes. Notice that instead of typing mob here, I type this. The reason for that is, what if we subclassed mob, and we wanted the repr to be untouched and to reflect the actual new name of the subclass type? Then this will actually give us the name. So I'll show you that just very, very quickly. And this should illustrate for you. So we'll make this a mob 2. Oh, IPython does not like my tabs. Tab. There we go. But if I had done this, you can see that's not what we want, right? So just a small thing to show you that when we override classes, there is some care that we need to take in order to make sure that if we haven't overridden something, the correct behavior comes through, and to show that there's some care that we have to take when dealing with overriding, some delegation we have to do back to the original base class. Additional things that we might have on this mob are properties. So say we have, let's say that we actually want to do something like constrain the mob into Cartesian coordinates. We don't want it to go outside of the bounds, and the bounds start at 0, 0. So one thing that we might do is we might do this, def x. And this is the getter, so, and this is the setter. Sorry, this doesn't take a value. So this is one thing that we might want to do with it. So then if we want to move this, m equals mob2, m.x equals 10. But if we do, and here we'll do a trick, if value less than 0, raise value error. Something pretty simple. So if we try and set this to -10, it'll blow us up. So that's one simple thing we want to do. We want to create properties so that we can get some, instead of having to write getters and setters, we have a much easier way to do this. The other common things that we might want to do are use class methods or static method. And class methods are merely methods where something like that. So maybe this mob represents maybe I'll put a type system here. So I'll say mob type, and this just returns mob type on the class. And so this is a mob 2, and I'll just do mob type equals bigger mob. And a static method is so class method is merely a method that doesn't require information about the instance. It's a method that only requires information about the class. And a static method is merely a method that doesn't require information about the instance or information about the class. So I have to think of a good static method for this that doesn't require information about anything. So it's fairly difficult with this example, but let's do bigger. And I'm just going to do this if, or I'll say distance. Return mob1.x minus mob2.y x squared plus, we'll find the Cartesian distance between two mobs. And instead of writing this as a top-level function, we decide we just want to put this in the class, in the namespace of the class, just for convenience. And I'll import square root from math. Oops, from math, import square root. So now we can get the distance between two mobs, and it's just there as a convenience. So if we have mob1 here and mob2 at some location, and we do distance m1, m2, there we go, and it gives us the distance between the two. Nothing complex. So all of this should be pretty basic and pretty straightforward for all of you. Is anyone confused? Oh, you're all perfect. So this is the standard way that we interact with classes. And this is the way that we're told to interact with classes, or the natural direction that we take when interacting with them if we come from a language that already has classes, Java or C++ or C. But one thing I'd like to say is that Python is, I said it's a very statically ignorant language, and it's also a very flexible language. So one thing that you might not realize that you can do is this is not really a class definition in the same sense that it is in a language like C++ or Java, where this is just defining methods that get constructed into an object, and those are just functions which exist at some space in memory that get inlined or jumped to. This is actually real executed live code, which means there's nothing wrong with me doing this. And I'm just going to create 3 stupid methods called A, B, and C. Sorry, locals A equals lambda. And this is a little bit tricky, because I have to do this. Okay? And now, and this should be x here. There we go. So this is actually kind of interesting, right? What I've done is I've now dynamically added methods to the class by just putting a for loop inside the class. And we could put for loops anywhere that we want in regular code. And Python doesn't restrict us to what we do. I could put ifs in here. So I could do, if I wanted to, I could say, depending on my game, I could say if game type is Euclidean, we do this distance function. Otherwise, we maybe do the Manhattan distance, where the Manhattan distance is, like Manhattan streets. So it's return mob1.x minus mob2.x. And we get the absolute value plus. This is if we're perhaps restricted to a grid, so that the distance between 2 mobs has to be you go over and you go up. You can't go diagonally. And then maybe I could say, object, and here's my thing, right? And now I can, let's get that, and we'll just remove that because we removed that code. And now if the game type is that, the distance function happens to be this distance function. Otherwise, the distance function has to be, otherwise if our game type is Manhattan, or I should say our board type, because this is really a restriction on the board. And if I change that to Manhattan, you can see that, oh, did I misspell Manhattan? Yes. And I'm from Manhattan. I'm not from, but I live there. I'm a Texan. And there you can see. So you can see that I can actually put conditionals inside the construction of the body. So one thing that this shows us, and a very fundamental thing, is that all objects in Python are these dynamically, it's all lines of code in Python are dynamically run with almost no static information. The only real static context we have is given to us by the parser, and the parser's context is very, very small. So it shows us that we can do some very interesting things that we can't do in other languages. We can dynamically create classes in some strange ways by using the exact same tools, conditionals, loops, that we use in regular code. And we might be tempted, I think that we've all been in a situation like this, but you probably, where you wanted to have some customized behavior on the class, but you put it on the outside. You said, if the game type's this, class body here, the game type's this, class body here. Or you used inheritance to set that up. But you can see that, like any piece of code in Python, anything can be dynamically, everything is run in a dynamic context. So you can do something as simple as writing code like that. So that's really some of the contours of classes. One of the additional contours of classes that I would like to show you that may bite you is the first thing that we're going to look at in the interpreter. So let me make sure that I have up-to-date code. So I believe I have Python 2.7.5 built. Yep, I do. And let's see that I have Python. Yep, there we go. So I have a Python built. And I'm going to show you something very interesting that may actually affect you in real code. Let's leave that there, and we'll create another cell. M1 is our mob, right? And it has a method on it called, I'll give it a method called move. Right? So it moves the instance from one place to another. Fairly simple, right? It's just a monster or some object that can move in the game. So I'm going to move it to a new point. Fairly simple. What is move? It's this bound method, right? And one interesting thing, and the first thing I'd like to show in the interpreter, is actually something that will affect the way that you write code, is something a little bit strange. If I do this, mob2 is mob2. That checks by equality that the mob2 object, the class itself, is the same as the class. If I do this, that's also fine. Now, if this were not correct, then we'd see a nasty little assertion error here. Move. Instance methods. This is the first very weird contour, and a very simple contour that a lot of people don't seem to run into until they start doing things with callbacks on instance methods. Instance methods in Python are dynamically created when you ask for them. A Python class doesn't have each instance doesn't have all of the instance methods itself that are bound to the instance living or that are created on the instantiation of the class. They're always created dynamically when you ask for that, which means that this function, m2.move, is created fresh every single time we ask for it. So you can see, I should use asserts more than prints. It saves me 2 characters. So you can see, and if I'm going to do the ID of these two just to show you that their locations in memory are different. So you can see the locations in memory are the same. The reason for this is no code has run in between, and so the moment that m2.move gets decrefed down to 0, it'll be garbage collected, and because instance methods exist on a free list, then we're going to reuse that memory location immediately. But if I put this in the same line, where it doesn't get decremented, where the reference count doesn't get decremented until the end, well, it does still. I have to stick this in a line where it uses them both. Oh, I know what I can do. Map. I can do this. m2.move, m2.move, and I'm missing a parenthesis. There we go, and you can see they're different IDs. So this is the first thing I want to show you, and it's a kind of weird thing. And if we go, so this is the CPython source code. You can download it at python.org. It's actually really well laid out. It's fairly easy to find things. You can start finding things just by grepping around. I can tell you for this example, if you look into objects and funcObject, you'll find PyMethod. So I'll use my Vim to find PyMethod new. PyMethod new is right here. And this here is the first piece of CPython code that maybe any of you have ever seen. And this is the code that gets called when you ask for an instance method. Before you call it, but when you ask the class, give me the instance method out, you can see that every single time it either creates a new one or it uses one off of this free list. This is just a memory optimization. But in each cases, it's creating this anew. And the implication of this is if you ever try and do a callback on an instance method, you'll find that the callback system that you want to use probably wants to have weak references to everything. You don't want to register a callback and that callback to hold on to the object if the object no longer exists. You don't want it to maintain ownership of that object. So you'll probably implement your callbacks with weak references, which is a very common thing to do. Because you have a weak reference on an instance method, the instance method will garbage collect the moment you register the callback, and you'll suddenly see that your callbacks are vanishing. And this is actually a very strange implication of the class model, because what it tells us is that in some cases we may actually have to manage the lifetime of objects ourselves. That is to say, in order to keep a callback on the object, we have to ensure that the object exists manually. Because the garbage collector doesn't have, you don't want the callback to enforce the object to stay around. But the instance method will vanish the moment you're no longer using it. So the only way to do this is to bind the instance method to a global name or to manage the lifetime of that manually. This is one strange consequence of the way that the class model works.
So the strong reference in the callback doesn't count as a reference?
So if you do callbacks with strong references, you're going to find that whatever's registering your callbacks is going to hold on to all your objects, even if those objects shouldn't exist anymore. So the easy trick that people use is they put their callbacks into a weak ref dict, right? Now, since there's only a weak reference to those instance methods, they'll be garbage collected immediately. You'll say callback.register, and the moment that line executes, there'll be nothing holding a strong reference to that instance method anymore, and it'll vanish. And your callback dict will no longer have that entry, and you'll realize your callbacks are no longer being registered. The reason that, for the most part, we have callbacks on top-level methods in the module level is because the lifetime of those is usually static. It's over the entire duration of the program. Nobody ever deletes, or people rarely delete top-level methods. So they exist over the course of the program, so it's safe to register a callback, or register it as a callback. Whereas with an instance method, the instance method comes into existence and goes out of existence with the lifetime of the class itself. So that's an interesting contour to the way classes work. And if you dig deeper and deeper into this, you'll see more strange corner cases around some things that you can do, especially around static methods and class methods. But this is my very quick introduction to classes. I want to show you a couple more underscore methods. And let me say, if you are a newbie to Python and you haven't spent a lot of time learning about underscore methods, but you are interested in all the different parts of classes and what they can do, we have in our audience a very accomplished speaker who has given more than one talk on underscore methods. Luke Lee. So I don't know if you're talking at PyTexas, but I've seen your underscore method talk before, and it's a very good talk. So please look him up, and there's a lot of information about underscore methods and the different things that you can do with the class object. One thing that I don't really want to talk about is old style classes versus new style classes, especially since I'm using Python 3 here. That's not an active area where anybody's really doing anything with classes these days. There is one use case for old style classes that's still around, that I think, which is what happens when you use these underscore methods and how the underscore methods are looked up. So the last contour I want to show you on classes is this. We have our class mob2. So I'm going to add another, I put this call on here just to illustrate one other useful, oh, did I not put it there? We'll put it here. It doesn't do anything interesting, it just returns a string, right? And I can use this to call M2 as a word function. But I have to evaluate this cell and then that cell, right? Nothing too spectacular. The interesting thing is, if I were to do this, will that work? And if I were to do, sorry, m1.call, oh, and I'm going to remove this. Oh, mob attacks fiercely. That doesn't work. So what I'm illustrating for you is how underscore methods are actually looked up. And this is one big implication and one very important thing about classes. And the driver for why we have new style classes as opposed to old style classes. So what I showed you is that, let's do this slowly. M2 is a mob2, and I'll make this an actual, we'll call it a monster. That may be a little bit easier to remember. And we'll actually call this a griffin, and we'll call this, what's another scary monster? A tesseract? What had the highest level and hit points in the AD&D manual? I don't remember. We'll call this, was it a tesseract? Does anyone know? Begin with a T. Yeah. Am I the biggest nerd in the room? Oh. Terask, yes. I'm nerd number 2 now. Great. Terask, right? So we'll replace a couple things in our examples. Terask. And if I spelled that right, I will be ashamed of myself. So there we go. There we go. There we go. And what's the type of a Terask? It's a monster, right? And this is an object itself, and this has a function called call on it. Terask also has a function called call on it. You'll see that it's just a bound method of that. I cannot reassign an underscore method on an instance. I can reassign an underscore method on a, so I'll do this, equals, whoops. This is, so new self. I can't do this assignment. I cannot assign an underscore method on an instance. I can only assign an underscore method on a class. And the reason for this, so if I do this and then I do Terask, the reason for this is new style classes. So let's see, new call, Shouldn't be able to do that. Or did they change that in Python 3? Oh shit, did they change that in Python 3? I don't think so. Oh, maybe they changed that. No, that's correct. So this monster attacks and monster flees. I cannot assign it on the instance itself. The reason for this is whenever we deal with underscore methods are always looked up on the type object. In some cases, what we'll see is that where you'd want to do overloading, like overloading of len, we don't actually go through the dictionary of the instance itself to look for things like a call or a len. We actually go to the type object. And in many cases, for things like, if this had a len on it, well, it's going to be difficult to add a len. Well, we'll add a len that gives the distance self from the origin. Right? If I were to do and I should do there. Got to return that. There we go. So that just gives a length. Well, we can't reassign this to something new. We can't reassign it to something new. The reason is, in the interpreter itself, there are things like len are done by looking up into the struct of the object itself, and they don't go through the standard protocol of getAttr and setAttr and things like that. And the implication of this is you can't do things like write proxy classes by writing a getAttr, a setAttr, and a delattr, and then delegating everything through those. Because you'll find that in the interpreter itself, there are cases where the interpreter looks at the type object, will look at the instance, get the type from it, and do direct struct access to the type object. And unless you can overload those, it won't work. So I'll show you the next interesting part of the talk. So that's kind of the contours of classes, some interesting things you can do. I'd like to show you what happens in the class construction process. And the tool that I'm going to use for this is a module that I really encourage you guys to use as often as you can, and it's the dis module. And there's a function in it called dis, and dis gives you the disassembly. It gives you the bytecode of some object that you're looking at, some function or class that you're looking at. I don't know if I'm being filmed here, so I have to be a little bit careful, but I often like to use this as my function that I'm dissing. But maybe we'll hold back today. Oh, this is my second favorite function name. How do you like that? Nobody? Come on, Def Jam? Oh, none of you were around in the 90s. So the dis module gives you the disassembly of some object. And we're going to see something very interesting when we do this. Here's a function called, and all it does is it returns a monster there. Or I should say create monster in the distance, please, could you? Now, that's a little bit too long of a function name. Guys are low energy today. I got to bring that energy level up to where I am. I'm sick too. I got to bring you guys up to here. So create monster. And what I want to do is I want to show you what happens when we disassemble the bytecode for this. And this gets to my other theme of how objects, or how the interpreter is actually very ignorant. And if we look at the bytecode, we'll see that there are almost no assumptions and no information about what this function does. So this is the bytecode for it. And you can see when you call create monster, it loads this global called monster. It loads two consts, the 10 and the 10, and it does this call function. And this call function is the delegation point for determining whether or not what you're calling is a Py object with an underscore call implemented, whether it's a class that gets constructed, whether or not it is a generator, and so forth and so on. So I want to show you this call function. And this is the second thing I want to show you in the interpreter. Namely, I want to learn about the interpreter, but I don't want to read the documentation. I just want to jump right in. And I have no idea where to start. This is how I started. I looked up bytecodes, and I grepped for them. And I'll do this a little bit better by doing, so we'll just do in C files. So I just grepped for those. And you can see that one file stands out, ceval.c. ceval.c is the main file that we want to look at when we're maybe starting our understanding of the interpreter. So this is for Python 2. Maybe I'll use Python 2 because I'm a little bit more familiar with the source code for Python 2. And the differences aren't going to be that different. Well, not that different. So I'll grep for call function, and if I go down far enough, we can see this is a big switch case loop which handles the interpretation of every bytecode. And we can see in this loop, this is what happens when you call a function. And when you call a function, you end up using this C function called call function. And call function ends up going through all this nonsense. And eventually, what you end up with is something that either turns into a fast function, a C function call, or a PyObject call. And you can see there's a lot of noise here, but you can pretty much step through what's going on here pretty easily. It says, is this a C function? If it's a C function, then go through the optimized route for calling C functions. Otherwise, maybe you want to go through the long route, like do a, where do I have, if it's a Py method, then you say get the method, and then get the function, and then you get the function object here, and then you call it using fast function. And if you just run through this, you can see all the different places where this one operation kind of gets delegated to the actual code that runs it. I want to show you what happens when we create a class in the same sense. So I'm going to do, instead of create monster, I'm going to create a monster type. And this is where we get to learn where metaclasses fit in. So instead of doing that, I'm going to do big or attackable monster. And the only difference between this and the regular monster is it takes some hit points and some other args. And maybe I'll add a property to say if the hit points go under 0, something happens. I'll add static methods to determine, is this monster stronger than you? I'll add class methods to give information about what the class range of this, what the THACO of this monster might be. To hit armor class 0, nobody? Oh, jeez. And I'll just do, this also shows one common pattern that we have when dealing with subclasses is that we always want to delegate to the base class itself. But I want to show you what happens in this case. So create monster type has a slightly different set of bytecode. And you'll see one very different thing here. You'll see load build class, and you'll see it do a load build class make function. Oh, this is Python 3. So load build class is slightly different. If this were Python 2, you'd see you'll see the bytecode I really want to show you, which is build class. And build class is our entry point into the building of a class, the building of a type. In Python 3, some of these pieces have been moved around, and so you can actually override the class builder. In Python 2, it's a little bit static. So let's go to in ceval.c. We have this build class bytecode. We have this function build class. And this is where metaclasses come in. This is really all a metaclass is. This little block of code right up here. So this should give you an indication that metaclasses really aren't anything magic. They're just merely part of a protocol, merely part of what happens when you create a class. And it's actually fairly simple. I'll step you through it. Metaclasses can exist at the top level. So that's what this is doing. It's saying, is there at the top level, sorry, that's what this is doing. Is there at the top level a metaclass? You get the globals and you see, is there a metaclass in the global scope? And it uses that. But it uses that as the third choice. The first choice it uses is, did you define a metaclass on the class itself? So did you do something like, that? Or did you do something like, that's all it's checking for. Did you define this in the dict of the object that you're being passed? And if you did, you use that as a metaclass. Otherwise, you see if any of your base classes you had a metaclass derived on them. And this is actually a very interesting thing that has some implications. You only check, if you have multiple inheritance and you have 1 class, 2 class, 3 classes, you only check that first one for its metaclasses. Which means that if you want to conceptualize multiple inheritance in Python, only that first thing in the list is a base class, and the rest are actually considered, the rest are actually mixins. So if this derived from monster, but also attackable, killable, something like that, this is a base class. And these two are really only mixins, because all the last two classes can do is give you additional methods. They can't give you any information about how you construct this type itself. Only the first one has its metaclass looked up. And that's what this is doing. And then all that happens, and this is the really neat thing, is the metaclass is merely some function that you call with the name of the class you're constructing, the bases, so the base classes of the class you're constructing, and the dictionary, just the methods that you've defined. And that's it. If we follow this, we'll see that the standard metaclass that we use is called type. And we can find that in object/ctype. And if we look at type, type itself is merely just a function that can create classes. And so if we look at PyType new, I have to remember what it's called. PyType, sorry, it's PyObject new. I have to remember where that is. No, it's in PyType. I'm wrong. Let's look for call. Oh, sorry. The names of these are slot, TP, no. If we look at the actual function that's called behind the scenes when we construct a class, we'll see that all it does behind the scenes is it calls the underscore new that you defined, then it calls the underscore init that you defined. We'll find it. Yep, call the init there. So all that's really happening in Python when you construct a class is you create a function that knows how to construct a class, and that goes off and uses this setup protocol to call a new and to pass the result of the new into the init. So one thing that I said at the beginning, one of the themes I wanted to stress was Python as a system language, where you have a system for the language, and you're free to interact with that at whatever depth that you choose. But one thing that this shows is that Python is providing you with a mechanism for creating classes, and then for creating classes that themselves can create instances. But there's no reason that you can't create your own class system, your own object system in Python. Because the one that's provided to you, all it is in the end, a function that you dispatch to, and that function, by convention, calls the underscore new and the underscore init. There's no reason that it has to work that way if you decide to build, at the user layer, your own object system. So I'll show you an example of this that's a little bit wacky. Isn't that what you want to hear when you're working and somebody's like, I solved the problem, but the solution is a little bit wacky? That's the first thing you want to hear, right? So, so let's see, Metaclass. So I have to grep for this. This is so this is in meta derived. Counting format. Meta derived, I believe. Oh, this is for derived metaclasses. Sorry, this is the trickier one where I do that one more time. Oh, inherit meta. So this is a very interesting example that I had for what you could do with Python to create your own object system. I have three classes, foo, bar, and baz. And each of them define their own members, their own data members. And here I have this interesting line here, where I take foo, and I union it with bar, and I intersect it with baz. And what this does is it creates a new class, derived. And derived has all the methods that foo and bar have in common, or rather all the methods that foo and bar have together, with whatever methods they have in common with baz. So it's doing the set union and the set intersection of the methods to dynamically create a new class. And you can see that this is something that we can't do with regular objects and with regular types. It's something that you can do in literally only 14 lines of code with a metaclass. And here you can actually see I've created my own object, my own base object. This is Python 2. And I'm actually using my own base object to create my own object system. So you can think that maybe there are some limitations. If you're working on a humongous system and there are some limitations with the object model in Python, you are free to, you probably shouldn't, but you're free to create your own object model if you want. And I think that if you look at that, because we're really running out of time here, but I think that if you look at that, you'll actually begin to see that some of the things that we take for granted or some of the things that we assume are just the way things are done are actually more along the lines of conventions of how the system works. These are things that we're provided that are conveniences, but we're actually free to code at whatever level we want. We can code in such a fashion that we still interact with standard objects in Python, but where we've created our own side system. In this case, our own side object system. And this may actually be useful, because what if, for example, you have a system where you have millions of different objects that have different fields, like information about financial data. And there's a million different fields on these different objects, just gigabytes of data. But each object that represents maybe the financial information about somebody's mortgage may have a distinct set of fields. And for some reason, and you don't want to have 100 fields on your object where only 5 of them are filled in. You want to do this sparsely. Well, you might be able to use a structure like this to dynamically create types that have only the fields that you know that your objects will have in order to save memory if you're loading enormous amounts of data. So that's maybe one possible use of this. There are almost certainly different ways to do it, or I don't want to say better ways to do it, but there are perhaps different ways to do it. But you can see that there's actually some flexibility around this. So I want to talk about, since we're very close to running out of time, I want to talk about the last thing. So I showed you kind of how metaclasses work and what they do. But there's one very important key part that I want to show you, which is what metaclasses really can be used for. In our mob example, we had some inheritance hierarchy. So I want to create a new monster called called boss, right? And this represents the end boss in the game, or one of the bosses in the game, right? And maybe the end boss has a prize, but he's otherwise just a regular monster. So when he dies, he farts out gold coins. And that's determined on his construction. So nothing too surprising. What I want to show you is that in some case, we might want to say that users are able to script our system live. Instead of being a MUD, we're now a MOO, where users are able to actually create objects themselves. And they're able to create their own monsters. They're able to write code against our system. Since they're not part of our development group, we want to make sure that there are certain constraints on the objects that they create, or the monsters that they create, so that they fit within certain guidelines that we've set for them. We can do this kind of constraining very easily and very flexibly in one way, but not the other. The way that we can do it very flexibly is if the derived class, boss, wants to put a constraint on the base class monster. So for example, we want to say, I don't want to be able to create this type unless monster has HP points. So I just want to make sure that my code will blow up the moment it runs if somebody changes that base class to change hit points to maybe endurance points or something else, or if they change the name of this field. Or I want to say that I don't want my code to run if the monster doesn't have the ability to, or if the monster is not also a subclass of mob, because I've made some assumptions in my code about this subclassing relationship. And I want my code to break the moment that those assumptions break. This is a way that the derived class is putting a constraint on the base class. The derived class is saying, I only work if certain constraints or guarantees are met on the base class. How do we do it the other way? How do we have the base class put a constraint on the derived class? How do we say, if you use my object and use subclass from it, you got to do these things, and I'm not going to let you create an object if you don't do these things? And that's what metaclasses let you do. There is one very common example of this that we should all already be using. Hast adder. HP. Monster doesn't have an HP? Oh, it's a dynamically created member, you're right. So we'll just leave. Is that not correct either? Oh, is subclass. I should have known from the syntax highlighting. There we go. So we'll create one more cell, and I'll show you that this is one thing that we can do. We can create this relationship where the derived class puts a constraint on the base class. And there's one case where this is already being done. If you ever see this in your code, maybe there's something wrong. And I wouldn't say that it's the use of is instance that's wrong. It's the checking that X is literally a list. Because in many cases, you don't care that X is literally a list type. You just care that it's something you can iterate over. And a tuple may be just as acceptable as a list if you're not mutating it. The better thing to do, and what we should already be doing, is using the abstract base classes in the collections module to check this. To check that X isn't literally a list, it's just something that I want to iterate over. That's all I care about. Or X is something that has a mapping relationship, or it's a sequence. We can more specifically add constraints to our code using isInstance by specifying this abstract base class to use, rather than asking for explicit things like, is it explicitly a list? Is it explicitly a dict? Because I'm sure we've all used code that explicitly checked for a list. But if you looked at the code, it just iterated through it. It could have been a tuple, who cares? Or it could have been a generator. And you had to do a conversion that was totally unnecessary in order to satisfy this very limited type checking. Using the ABCs in the collections module, you can still put the constraints that you want without having to add unnecessary constraints, like constraining against a static type. Additionally, we have in the collections ABC module abstract base classes, where you can do things like create an interface, and you can say, this is an abstract method, and you can't create a class unless it implements these methods. One situation that I want to show you with our mob example is, what if we don't want you to be able to create a monster who can ever have a value, who can ever move outside of the arena? So we want to say that you might override our X method or our Y method, our move method to move it around, but we don't ever want you to be able to move it outside the arena. And we can do this with metaclasses because, if you remember, when we looked at that build class, the first thing it did was it looked at the metaclass on the first base class. And as long as our users don't create their own metaclasses, so this isn't a strict security mechanism, but this is a mechanism by which we can stop people from making mistakes which they don't want to make, we can use metaclasses to do that. So I'm going to show you an example of that. So let's figure out where I put that example. Oh, metaclass order, I believe. Oh, no, that's this one. So I'll show you an example of that I have, because I don't know if we have time to type it up ourselves. Oh, yeah. So this is an example of, no, that's not the one. Otherwise, we'll have to type this up. Oh, that's a shame. OK, so we can do this ourselves pretty easily. So let's say that here is our base class, and it has a metaclass on it. What we can do in this is we can this new function is what happens when you create not an instance of the class, but when you create an instance of the type, when you subclass from it. So we can put constraints here. So I'll show you what happens when we don't do anything interesting. And you can see that we have a hook for adding these constraints. And this always blows me up. Here we go. So, and this should be metaclass type. Oh, and this is no longer allowed. They changed a couple of things in. Oh yeah, yeah. Who's that in the? Is that Nick? Because I heard an Australian accent. Yeah, they changed this around on me just to blow up my talk. Can't believe it. Name, basis, body, return, type.new, name, basis, body. There we go, and this should be that, and this should be, we'll just do it on the init. And we'll just do args, because we're running out of time. OK, so, and this is base, metaclass equals metaclass. Oh, type, what did we miss? Oh, and this should be, yeah, there you go. There we go. OK, so what's happening here? So basically, whenever the metaclass code gets executed, we're printing out what it's executed with. And you can see that This is printed on the declaration of the class when that code. So we saw in the first example that we can add for loops into our code. We can add conditionals into our code. And that gives us an intuition that this is actively running code. It's not just a definition. It's actually currently executed code. When this is currently executed, this will be called and this code will be run. And you can see that it's printing this out. And when this is executed, this code will be run here. Because derived derives from base, and base has a metaclass, derived will use that metaclass in its construction. And it is here where we can hook in any constraints that we want. So a real constraint that I've seen in practice is I had a unit test suite, and in the unit test suite, I need to do some special database connections. I needed everybody to subclass from our unit test suite. And I suggested that we make a constraint that if you do anything with a database connection in your test suite, that in the construction of it, we assure certain things. Like if you have a setup method, we assert that you must call our setup method. And instead of forcing it by looking at your setup method, I would just wrap their setup method with a new one, which did the database initialization. And that way, whenever you derive from my class, I wrap certain methods of your class to get the behavior that I wanted. In this sense, the base class is putting a constraint on the derived class. This wasn't what actually ended up being done. What they did instead was they assigned 3 people to write reports and to email people all day long, grepping through code to see, did you call the right setup method in your classes? But you can see, with metaclasses, you can very easily enforce a constraint on a base class because you have a hook into the construction of that class, right? So what I can do, this should be what, self, name, bases, body? And that should be self, name, bases, body. So I'll show you an example of a simple one. I don't like your name, right? So now I can't create a base class called derived. You can see I can do that. Now I can put any constraint that I want on the construction of this class. So I could say derived doesn't have this method. I don't like it. Or if you try and override my move method, I just throw it away and I use my existing move method. I can put any constraint that I want in this, and that's what metaclasses are really used for. That's the tool that we can use them for. Anytime we see a problem that can be modeled as a constraint from a base class to a derived class, metaclasses are really the only tool that we have for that. So we've totally blown the time that we have. I'm going to show you 3 things, and then we're all going to go have lunch. And I can show you a bunch of other interesting examples of this while I'm scarfing down my kolache roll. The first thing is, in Python 3, simple enum. So simple enum has some very interesting, or the enum type has some very interesting behaviors to it, such as you can create an enum like this, and you can actually iterate over the class itself. Not over the instances, but over the class itself. And that's actually a very easy thing to do. All you do is you add to your metaclass an iter. And when you add to the iter, what that'll do is it'll put the iter on the type object, or rather on the type of the class itself. And when you try and iterate over it, it'll go off and it'll find this. So this is one of the hooks you can have to add methods, not to instances of the class, but to the class itself. So that's this first behavior, fairly simple to do. And then I can just print those out. Additionally, I might want to OR them. So you can see that all that requires is putting these methods on the type itself. And then finally, one feature that this doesn't have, because this is written in Python 2, that Python 3 has, is that the order in which these are defined is the order in which they're iterated over. So I'm going to show you that this doesn't have that property. Notice I did strawberry, chocolate, and vanilla. And this pulls them out in, we'll just clear that. This pulls them out in order of, oh, I actually assigned numeric values to them. See 1, 2, 3 here, and I think these pulls them out in order of 1, 3, 2. So those are the actual values of the enum. I was doing an integer enum, but I'll make this berry, chocolate, vanilla. And you can see these come out strawberry, vanilla, chocolate. They don't come out in the right order. And this is one of the features that they wanted on the enum class. And in order to do this, they added a prepare method. So the dictionary in which you create methods on a class through the metaclass is now something that you can control, and you can make it so that the methods that you create in the body of a class are put into, say, an ordered dictionary, and so they come out in the right order. The other interesting thing that you can do is Python 3, Python ceval.c, build, I want to go into the built-in module. You noticed when I did the dis on it, it said load build class. What that was doing is loading a built-in called build class. So now this first function that we hit in building the class is actually something in the built-ins module that we can overload. So if any of you were around before import hooks, you may remember that the way that we were handling custom imports was to overwrite underscore import underscore. You can do the same thing for classes. So you have a hook into the construction of all classes. If you were to hook this at the beginning of your program, you might be able to, for example, log all the times that people define types in your program. So that's another interesting thing that we can do. We have so totally blown the time that we have, I feel that I have to cut this short. And I'd say that if you have any questions, please feel free to email me. I'll be around today and tomorrow. My email address is at the top, james@nycpython.com. My name is James Powell, and I hope this was a useful introduction to both classes and metaclasses in Python 2 and Python 3.